Graphs of transformations. You have this sheet, and then you have a peach-colored sheet. Should we call it the peach sheet? Just so we're on the same page. The peach sheet. Okay, that's the peach sheet. All right. So it kind of sounds like cheat sheet. The peach sheet. Okay. So I want you guys to be looking at the bottom of your notes sheet because that's the only one that has like really a lot of room. So down here, this is your like quick quiz. It's not graded. I just want to see how much you know. Okay. And don't cheat because these are on your peach sheet. So flip it over, so that you have the grid exposed and not the other side. All right. So we have different types of functions, and I want you to like graph what these different types of functions look like. So a linear function is like y equals x mainly, okay? Graph what he looks like, ish, okay? Graph what he looks like, ish. All right, then I'm going to start writing smaller. Quadratic functions are y equals x squared. Graph what he looks like, ish, okay? Then you have cubic functions. I'm going to write all these up here, and then you can figure out what the graphs look like, okay? Or do the best you can. We will fill these in here in just a second, but I want you to take a nice stab at what you think these look like. Cubic. Then you have quartic, which is y equals x to the 4th power. And then you have quintic, which is y equals x to the 5th power. And I could keep going on forever, but we're going to go over to something more interesting, like absolute value. Is y equals the absolute value of x. And what does he generally look like? And, oh shoot, what are some of the other ones? Like a square root. Square root is y equals the square root of x. And what does he look like? And a cube root, or y equals the cubic root of x. What does he generally look like? And we'll do one more. This is a rational function. Is y equals 1 over x. What does he look like? Okay, and I'm going to do one more on this side. So above linear, we're going to do a constant function, like y equals 3. What does he look like? Okay, there's all those types of functions that you should have like in your toolbox of like knowledge of what functions look like. Okay? Graph me what you think each one of those looks like. Okay, don't cheat. I think I got all the main ones on there. Yeah. I'll give you a couple seconds. If you're watching this video and you want to fast forward, great. I'm going to give them a couple seconds to fill in what they think these look like. Gravity. Take a nice good stab at each one.
Yeah, I'll look the same.
You don't have to go which two.
Mine look right.
Oh boy, kid, you got some messy.
Let me see what you're thinking.
Messy.
One looked like a snake.
I'm just gonna look at it right now.
If you don't know them, now then you will know, and then you'll like be able to remember them. Remember them better, right? You'll know which ones you don't know, and then you'll know them better, right? Okay. Yeah. Okay, so I'm gonna start. Linear looks like this. In general. Now, when you start to add numbers in there, he gets to be taller and skinnier and whatever, or shifted over. Doesn't necessarily go through 0, 0, but linear function generally look like that. What's a quadratic function? A parabola. He looks like a U, okay, in general. Then we start to move him around and do stuff, okay? Cubic, what's he look like? Like a sideways, maybe S-ish, something like that. I don't know how you describe that. I actually describe that as like a quadratic function, but you've taken this little side right here and moved him down. That's exactly what he is. He's like two halves of a parabola. One's going up and one's going down, right? Exactly what he is, okay? Now, a quartic function, what's he look like? A W. He has an extra little hump in him, okay? An extra little hump. A quintic function starts here and he goes like this with an extra little hump in him, okay? Now, I always stop after this section because a cubic, a linear, and a quintic, like 1, 3, 5, 7, 9, whatever, any odd functions are going to look similar to each other. They're going to start down here and end up here, start down here, end up here, start down here, end up here. Their end behavior will be exactly the same, right? If I asked you what x to the 101st power looked like, it's going to look something like one of those three, right? It's going to start down there, end up there. You can figure that out, right? Same thing with quadratic and quartic. Squared to the 4th power, to the 6th power, all of them are going to start up here, end up here, start up here, end up here. Unless they're negative, then they're going to start down, end down, right? They all have the same kind of end behavior to them, all right? Absolute value, what does he look like? A V. Exact 45-degree angles until we start stretching him out, okay? Exact 45-degree angles, yeah. Square root, what's he look like? Meow. That thing. This thing, okay? He stops here. He does not go on forever that way. Why? Because he doesn't. Why? Can't be negative. You can't have a negative inside of a square root. Okay, cubic root. What's he look like? He's not quite as tall as what a square root function looks like, but he goes back the other direction because you can take the cubic root of a negative number, right? Yeah? But you can't take the square root of a negative number, right? Like the cubic root of negative 8 means what can I take times itself 3 times to get negative 8? What's that? Negative 2, right? I can take the cubic root of negative numbers, but not square roots, okay? Now, it is no coincidence that cubic root and cubic functions look very similar to each other, just the opposite way, right? Yeah, that's not a coincidence. That is like the way it is. A rational function, 1 over x. The love on my poster, the L, right? But he's also, not only is he here, he's here also. We call these the boomerang equations. If you want to go ahead and put like dotted lines in here, there are dotted lines there. Do you know what those are called? Asymptotes. Those are lines that never crosses, right? Okay. We talk about rational functions later on in the year. But that's what those are. And then constant, I added him last. What's he look like? Straight horizontal line at whatever this value is. So if it's at 3, that means it's crossing here at 3, and it's not, like, it doesn't have any slope to it. Okay? Now, these functions are basically what all of the functions start with, right? And then we start adding numbers in, and it starts, like, shifting them to the left and to the right, or up and down, or making them taller or skinnier or shorter and fatter and that type of thing, okay? So that's what this peach-colored sheet is talking about. And we filled this out before, have we not? Yay! So you know these rules already. Great. So this should be really, really fast review. We are going to fill in this column, this column, this column, and then everything before that. So the last 3 you can kind of like skip because they're basically the same thing. I don't want to like beat a dead horse, okay, because it's already dead, right? So we don't fill in the last 3 columns because it just gets too repetitive, right? So this is a linear function, and we're going to look at the effects of a translation 6 units up on a linear function. We're going to do the same thing here when it's a linear function that's not just x, and a quadratic function, okay? Quadratic. Okay, we'll see what all of these rules look like, okay? I think I'm going to fill in all 3 of these at once for each one, and we'll see what those look like, okay? So if you're going 6 units up, if you're taking a linear function and you're moving it 6 units up, what will that look like in the equation? X plus 6. X plus 6. And I'm going to be really lazy and leave off my y equals on each one, okay? But just keep in mind that this is like y equals x plus 6 is what it changes into. I just don't want to have to write y equals every time. So y equals x plus 6, okay? Let's do the bottom one and then we'll go over, okay? 5 units down, what will he look like? X minus 5, just tacked on the end. Okay, now let's do the middle column. So I have 2x plus 3, and then I'm adding 6. So that will actually be 2x plus 9, right? So it's going to be a little bit different when you have a linear function that's not just y equals x, right? You have to actually like do some computational things to get him simplified, okay? And this will be 2x plus 3 minus 5, so he will be 2x minus 2. That's what his function will look like, okay? What about x squared? What will that look like if you move him 6 units up or 5 units down? Plus 6 inside or outside the square? Outside. He'll just be x squared plus 6 and x squared minus 5. basically we're just tacking those numbers onto the end. Tacking those numbers onto the end. Okay, now right and left. If you're going right and left, how does that change from going up and down? Do you remember these rules? To the right is minus. Okay, I always have you put a little star over here. I have my algebra kids put a little star that goes for both of these because you use the opposite. I can't spell opposite. O-P-P-O-S-I-T-E, sign. So basically, when you're going to the right, you think positive, but it's actually negative. Okay? Up is positive, down is negative, but right is actually negative. Okay? And I'm going to go ahead and put x plus 6 in parentheses. Okay? And x minus 5 in parentheses. Okay? Now, for a linear function, for when it is just y equals x, okay? Doing y equals x plus 6 like this and y equals x plus 6 like this is no different. Does that make sense? The parentheses are not really doing anything unless there's a number off to the side here, okay? And the reason for that is this, all right? A linear function looks like that. That's just the original y equals x, okay? Now this guy says up 6, right? So if I move this thing up 6, he will look like this. 1, 2, 3, 4, 5, 6. Yeah. 1, 2, 3, 4, 5, 6. Oh shoot, I didn't do those right because that was 9 and 4. But anyway, up 6 looks like this. Okay? But is that not also the same thing as taking this guy and moving him to the left 6? Right? Isn't that the same thing as moving him to the left 6? Okay? So up 6 and left 6 are the same thing when you have a linear function that's just y equals x. Okay? I did these ones over here wrong. Did you guys notice that? Because it's not 6, it's 9, and it's supposed to be minus instead of plus. Blah. So I did that wrong. 9 units right will actually be x minus 9 in parentheses. And 4 units left is x plus 4 in parentheses. Yeah? Does that make better sense? I'm trying to change the rules on you and it's not changed. Okay? So when it's 2x plus 3, like the middle column, how do you do those? Okay, the plus and minus stuff goes inside of where the x is. So instead of it being 2x plus 3, I replace that x with x minus 9. That's how he works. Does that make sense? I replace that x with x plus 4. Instead of it being 2x plus 3, I replace it with x plus 4. Okay, now, if we distribute that, it will be 2x minus 18 plus 3, or 2x minus 15. That's how he will change. Okay, so it's a little bit more tedious and a little bit more work when you have stuff that you're plugging in, or like horizontal translations that are in parentheses when you're simplifying. Okay, this bottom one, 2x plus 8 plus 3, which is 2x plus 11. I'll zoom in so you can see these a little bit better. Whoa, maybe. Does that make sense? Yeah, when you simplify? Maybe a little bit? Okay. Now, what does the quadratic column look like? What does the third column look like? If we went 9 units to the right. It's still going to be x minus 9, but how is it different than like one of these two up here? Okay. X minus 9 is now inside of the parentheses, like that. Okay? X minus 9 inside parentheses. Do not FOIL these out. Leave them like that. Okay? Like this column we simplified because it was easy. Do not FOIL each one of those out. Okay? What will the 4 units left look like? X plus 4 in parentheses squared. Don't FOIL. Just leave it. Okay? Good? All right, now, let me combine some of this stuff. We were talking about yesterday, whatever, in section 3.3. We would have things like y equals x minus 2 squared plus 3. Okay, that's a combination of horizontal and vertical translation. So the x minus 2, how is that moving it? Horizontally, 2 to the right. So that's moving him 2 units to the right, and the 3 is moving him up 3. So basically my parabola is 2 to the right, up 3, and I have my vertex, and he looks like this, okay? That's why they call that vertex form, is because I can figure out where my vertex is located. It's located at the point 2, 3. Does that make sense? Yeah? Okay. So it's because of these transformations that that vertex form exists like that, okay? All right, now we get into the ugly stuff, vertical stretch and compression. Well, maybe not. Vertical's not bad, horizontal's ugly, okay? Vertical stretch and compression, if you're starting with y equals x, what does vertical stretch by a factor of 5 look like? Y equals 5x. Okay? Basically, instead of him going up 1 over 1, up 1 over 1 for a linear function, he's going to go up 5 over 1, up 5 over 1. That's going to make him tall and skinny, right? A vertical compression by a factor of 1/3, what's that look like? 1/3 x, okay? He's going up 1 over 3 now, so he's going to be a little bit shorter and fatter, okay? Now, how does that change when it's 2x plus 3? The 5 is on the outside, and you're multiplying by 2x plus 3, so it's 10x plus 15. Well, don't put parentheses there, okay? 1/3 is 1/3 times the whole thing, so 2x plus 3, and that will make 2/3 x plus 1. Okay, I'll slow down here real quick. So the 5 is basically being tacked on to the very beginning. The 1/3 is being tacked on to the very beginning, and you're multiplying those through. Okay? All right? What does it look like with x squared? Take a guess. What does it look like with x squared? 5x squared and 1/3 x squared. Okay, just tacked on at the very beginning. You're not actually squaring the 5, and you're not actually squaring the 1/3. That's what we're going to be doing next. Okay. Okay. All right. Horizontal stretch and compression. This one, we're stretching it by a factor of 2, and then we're compressing it by a factor of 1/4. Okay. Up here, when we were doing horizontal translation, funny business happened where we had to change the sign. Funny business is also going to happen down here when you're doing horizontal stretch and compression. Anything horizontal has funny business. Okay? Horizontal translation, opposite sign. Horizontal stretch and compression, you use the reciprocal. Ugh. Use the reciprocal. Okay? So if we are doing a horizontal stretch by a factor of 2, what's the reciprocal of 2? 1/2. Okay? And I put the 1/2 inside of parentheses. Okay? For a linear function, it doesn't really make that much of a difference, because 1/2 x in parentheses is the same thing as 1/2 x out of parentheses. It doesn't make any difference, but it will later on, okay? What does the second one look like? Horizontal compression by a factor of 1/4. 4x in parentheses, okay? Now, I put it in parentheses over here so that you can remember to put it in parentheses over here. What will this guy look like when it's 2x plus 3 is what we're starting with? 2 parentheses 1/2 x plus 3, right? It's 2x plus 3, but we're replacing it with 1/2 x. So that will actually make it x plus 3. Okay, then the next one we're plugging 4x in, so 2 parentheses 4x plus 3, which will make it 8x plus 3. Is that super confusing? No? The more you have these, the more they'll make sense. The more you do these, the more they'll make sense. Okay? What will the quadratic look like? Easy, you think? 1/2 x is going to go inside parentheses. Okay? But then 1/2 squared is 1/4. So if you want to get it out of the parentheses, which I would encourage you to do there, you don't have to FOIL or anything, you just have to distribute the square. It actually comes 1/4 x squared, right? Now in the next one, we're plugging 4x in parentheses, and we're squaring that, so that will become 16x squared, right? 16x squared. Okay? All right, reflection. When you're reflecting something across the x-axis, here's what it looks like. Y equals negative x. When you're reflecting something across the y-axis, y equals negative x. Those two things are not different from each other for just a linear function, right? But when you are starting with 2x plus 3, this one, you're putting the negative in front of the whole thing. This one, you're just making the x negative, okay? Stop there for a second so you can absorb the difference between those two, right? The one, you are making the entire thing negative. Across the x-axis, this entire thing is negative. Here, you're just making the x negative. So what does the top one simplify to? Negative 2x minus 3. This one is negative 2x plus 3, okay? So it does make a little bit of a difference, all right, when you're dealing with functions other than just y equals x, okay? Now over here, this guy. This is y equals x squared, so I do y equals negative x squared. I just put the negative in front of everything. But then this one is y equals negative x squared in parentheses. Okay? Now, that bottom one, if I take negative x and square it, that's like negative x times negative x, what will happen? It will become positive, right? So you mean to tell me that if I start with y equals x squared, which looks like this, and I reflect that across the y-axis, it will look exactly the same? Yeah, right? That just kind of makes sense. Right? If I take this guy and reflect it, it will be exactly the same function. Okay? Now let's go over the rules. Just real quick. Okay? When you're doing a vertical translation or up or down, are you adding and subtracting or are you multiplying? When you're doing a translation, up or down, you're what? You're adding and subtracting. So we're going to put an x in that column. You're not multiplying. And are you doing it inside of the function, like inside parentheses, or outside the parentheses? Like tacked onto the end of the function? Outside. So this is like the little key code here. Okay? Now a horizontal translation. Adding and subtracting or multiplying? Adding and subtracting again, but this time you are inside the function, right? You're doing it inside of parentheses, like the 2x plus 3, you had to put the x minus 9 inside the parentheses. Yeah? Okay? Now, vertical stretch and compression. Are you adding and subtracting or multiplying? Multiplying. I'm multiplying by 5, multiplying by 1/3. And am I multiplying it outside of the function or inside parentheses? Outside. The 5 is being multiplied on the outside of the entire thing, right? Outside, outside. Okay? Horizontal stretch and compression. Still multiplying again, but this time we are inside the function, okay? And the last one's reflecting over the x-axis. Am I multiplying or adding? You're multiplying. You're multiplying by like a -1, right? For both of those. But when you're reflecting over the x-axis, you're outside the function. When you're reflecting over the y-axis, that negative goes inside with the x, right? Okay, so let's look at the, like, how this strips down here. When you are translating, you are adding and subtracting. That's the trend there. When you're stretching, compressing, you are multiplying. Okay? When you are doing vertical, what's the trend there? You're doing outside of the function, whether you're adding, subtracting, or multiplying. When you are doing horizontal, you are inside the function. Does that make sense? Yeah? So that's like how that breaks down, okay? Now, you can take any function that like is broken down like that and decipher, since you know what the parent functions look like, that's what these guys are. If they add numbers or like throw numbers into those equations, you can figure out what those look like and shift them that way, as opposed to having to make a table of values and plugging in -3, -2, -1, 0, 1, 2, 3, and plugging them into the equation and then graphing. You can cheat because you know the rules, and you graph them, and then you're done, and then it is nice. Okay, that's a lot. We'll stop. Yay.